Okay, so we've spoken about induced electric current. The first thing that we need to deal with induced EMF or electric current. What did we say? First of all, Faraday's law, and I'm just going to read it out to you as I've got it in your textbook, which states, the magnitude, in other words, the strength of the induced EMF in a coil is proportional to the rate of change of magnetic flux. Okay, what I'm going to put it is an EMF will be induced in a conductor. It doesn't have to be a coil. It can be any conductor. It can be a straight piece of metal like this, okay, with or without a complete circuit attached to it. It doesn't have to be a full coil. Your textbook talks about it as if it was a coil, right? Or a coil like this. Get different types of coils, but it doesn't have to be. It can be any conductor, complete circuit or not. An EMF will be induced in a conductor when that conductor, and let's just get the wording the same as your textbook, experiences a change in magnetic flux linked to the conductor. I'm not going to say linked to the conductor. Right. Faraday goes on to say a bit more than what your textbook states, and that's why I'm not keen to say that is the definition. I want to double check on what the exam guidelines state, okay? Because I know that Faraday's law says more than what your textbook states. It goes on to say that not only will an EMF be caused, but that this EMF is proportional to the rate of change of magnetic flux. Okay. This EMF is proportional, not directly proportional, to the rate of change of magnetic flux. Yes. Move the magnets. No problems. You get some dynamos where instead of having a coil that spins around, okay, normally you've got a magnet, and then in between your magnets you've got a coil that you turn in a handle, like that one that we use inside to shock people. Okay, you've got a coil that turns around with two magnets surrounding the coil. Others have got a coil of wire, and when you turn the handle, you actually turn in a magnet inside the wire. So as long as the one changes relative to the other. So that's a good question. If I held this, yeah, and I took the one magnet or both magnets and moved them, okay, you get the same effect. You can either move the magnet or the coil. So in other words, the EMF will be induced in a conductor when that conductor experiences a change in magnetic flux. Doesn't matter how that change of magnetic field lines is experienced, either you move the conductor or you move the magnets. Same thing. Yes.
I can understand that if you want to use the current to the current, you can see that you have to increase the
if you want your motor to work nicely and not go that type and turn in jerks, then your motor must be tuned in. Because what happens is, if I'm doing, let's just have a look at this. I'll move it this way. Which way is the current flowing? Let's just say in this piece of metal. I do that. Which way does the current flow? Let's say towards me. I move it up. Which way does it flow? Away from me. I move it down towards me. Up, away from me. Down, towards me. Now what did that do to a motor when you're sending this current through a motor? The motor's going to go whoop, whoop. Is it going to keep turning? Your motor's going to go up and down. As your current changes direction, your motor's going to change direction, isn't it? No. Let's say your current's only moving, I'm doing it by hand. Once, 1 second up, 1 second down. 1 second up, 1 second down. A motor can easily move, okay, like that. So you've got to sort that out. So what you do with an AC motor, instead of having permanent magnets, you have magnets. So if your current flows in one direction, this is north, this is south, current's flowing through your coil that way. Your current turns the other way, this is north, this is south, so it all works out and your motor keeps turning in the same direction. That's how an AC motor works. Okay, did that answer your question? So AC motors are a lot more difficult to manufacture than a DC motor. Yes?
Wouldn't it be some cases where the motor, because the first movement it has is in one direction, and if the movement of the thing is relatively fast, so wouldn't the first movement have momentum over the second movement to be able to turn that way? Like in one direction?
No. If you try to run a DC motor off AC, it won't work. It'll just shudder. Okay, that's all it does. Now, you've got to turn this dynamo. Okay, and we're going to talk about that, because the faster you turn the dynamo, the faster your current vibrates back and forth. If you turn the dynamo slowly, your current goes zoop, zoop, zoop. Turn it faster, it goes. Okay. Now, how fast does the guy at ESCOM turn the dynamo? Yeah, they got a bunch of guys on treadmills there. How fast do you think that guy is able to turn it? Okay, they got a whole lot of them turning it. They turn them at 50 turns per second. Okay, try and turn your finger around 50 times a second. Can you get it more than once a second? Okay. Those dynamos, now the dynamos at ESCOM, a typical armature would be the size of this building. Okay, the size of this building. And they've got lots of armatures. And that armature is turning around at 50 full turns per second. You don't want to fall into it. Okay? You think a blender makes a mess of a frog? Okay? You'd be vaporized. Okay. 50 turns in a second, something the size of this building. Can you imagine if it suddenly starts developing a speed wobble? It will just take that building out. Now, how does that guy turn it? Now they've got a whole lot of guys working on it. They use dynamos. No. What? They burn coal. How does burning coal make it turn? They create steam. That's what they're doing. So that's the only reason you use coal or oil or petrol at a power station, is to boil water. And then the water that boils gives you steam, and the steam turns the dynamo. Okay, high pressure steam. What's another way of boiling water if you don't have coal or oil or nuclear? Okay? They have a nuclear reaction happen. Nuclear reactions give off a lot of heat. Okay? You could use this much uranium and would probably give off as much heat as 100 tons of coal. Okay, so do you see why the future is nuclear, unfortunately? Okay? I'm not saying nuclear power stations are perfect at this stage. That's the only way this Earth is going to survive with nuclear power. Okay? Nuclear power, this much uranium will produce more heat or boil more water than 100 tons of coal. Okay. So, think of how much pollution 100 tons of coal causes in mining it, in transporting it, in burning it. That goes off, it causes just as much damage. Yeah. Okay. But your nuclear reaction gives you heat. What do they do with that heat? They boil water. That's all they do with that heat from the nuclear reaction. They boil water. They have a cup of tea. Okay? And the steam turns the dynamo at how many turns a second? 50 turns a second. That gives us our alternating current, which is vibrating back and forth at 50 turns a second. That's it. Simple. Okay? Does the nuclear reaction come into contact with water? No, there's water around it. And this water boils, and the steam turns the dynamo. But they need to cool the nuclear reactors down, because that water that turns into steam doesn't cool it down. Where does the water come from that cools the nuclear reactors down? At Coburg? The ocean. So is our oceans come into contact with radioactive material? No. If the radioactive material is in a container, it's sealed. The ocean flows around it, cools it down. That ocean water is about, I think, 4 degrees warmer when it goes out than when it came in, which is a massive change. Okay. The steam also doesn't come into contact with the nuclear reaction. That turns the dynamo. That water is cooled down again and reused as steam, etc., etc. Seawater is not used up. It just comes in, flows around it, cools it down. The other water is boiled, steam, turns the dynamo, steam is collected, back in. And that's our nuclear. So no nuclear waste is escaping into the atmosphere. At the end of a few months, they combine the nuclear waste into blocks. They pack it into big concrete, bigger blocks. They travel it up into the Kalahari Desert, and they bury it about 50 meters below the ground. And they hope that we're all gone long by the time that starts causing problems. Okay. It's not the ideal solution. Not an ideal solution. How else? Yes, people are talking about sending it off into space, but space is already overcrowded with waste. Okay, people are already picking up problems with waste in space. I'm not too sure what the actual final result will be. So, okay, let's have a look at that. So, that is Faraday's law. Now I'm going to give you another law, okay? And not Faraday, but also starts with an F. Fleming again. How many? Which hand? What was his left hand? Left hand. Motor rule. This is his right hand. Dynamo rule. Thank you. Timon, have you got it in your head or on your paper? Didn't say you had to take it down. I said I would give you notes. Fleming's right-hand dynamo rule. Now, let's just have a look at a setup here. We've got a magnet, north and south. Okay? We've got a conductor. There we are. Which way is that conductor running? Is there any current flowing through that conductor? Not yet. That's just a conductor that is running into the board there like that. I'm going to lift that conductor up. Okay, now, we said there are how many fingers that you work with in your right-hand rule? No, we're not talking with the right-hand rule. This is, I'm going to, okay? It's exactly the same as the left-hand rule. Okay, we're talking about the right-hand rule now. Okay. What we are trying to decide is, if I take this piece of wire and I lift it up, is the current going to flow out towards you, or is it going to flow in towards the board? That's the question. Okay, so thumb is thrust. Which way is the thrust in this case? Down or up? Up. Which way is the field? Left to right. Okay, so thrust is up, field is that way, you all agree? The current will be flowing into the board. So how should I represent that conductor? Current flowing into the board. Those are the tail feathers at the back of the arrow. Okay. Let's have a look at another one. There's your conductor. Let's move it up. Right, so there we are. There's your conductor. We're moving it up. We want to know, is the current going to flow out of the board or into the board? Right hand. Which way does your field go? Right to left. Which way is your thrust? Up. Which way will it be thrust? Out of the board, so I leave it as a dot representing an arrow coming towards you. All understand this? I want to do one more.
So why do we even have the vector?
Because that's for the motor.
So that Dynamo.
Right, there we are. Here's your wire. We're thrusting it to your left. Is the current going to flow towards you or into the board? Which hand do we use, Shara? Right hand rule. Why are you using your right hand rule? We're trying to find out which way the current will flow. In a motor, we know which way the current's flowing. We're trying to find out which way the movement is. Yeah, which way is the movement, Matthew? To the left. Okay, so right hand, field is up. You agree? Thrust is to the left. My second finger, which tells me the direction of the conventional current, is into the board. So how must I represent that? With an X, the tail feathers of an arrow. Right. Do we all understand Fleming's right-hand dynamo rule? Okay. Is there anyone who is confused between the right-hand dynamo rule and the left-hand motor rule? Who doesn't know why we've got two different rules? Sherwin? Why do we have two different rules? In a motor, what are you trying to find out? The direction that the motor will turn. With the left hand, you're trying to find the thrust. You know which way the current's flowing because you can see the battery. You know which way the magnetic field runs from north to south. You're trying to see which way the motor will turn. Thrust. With the dynamo, you're putting in the kinetic energy, so you know which way the thrust is. You know which way the magnetic field is. You're trying to find the direction of the current. So with the dynamo, we use the right-hand rule to find out the direction of the current. With the motor, we use the left-hand rule to find out the direction of the thrust, the way the motor turns. Yes?
Very serious, because I'm very confused about one thing. If we pretend, our first example, that we didn't have the thrust indicated,
But I gave you the direction of the current.
how would we find out where the thrust?
Whoa. You'd use the same rule. Okay, now we know the answer's up. Hey, Timon? Okay. Because, of course, I'm not going to give it to you straightforward in an exam. I'm going to ask you back to front. Here is a dynamo. Okay? You've got a piece of wire there, and the current is flowing into the board, into the page. Which way has this conductor been moved in order to achieve that? So now which hand are you using? Right hand, because it's a dynamo. What are you asked for? The direction of the thrust. So you want to find out which way your thumb is going to point. Okay, point all your other fingers in the right direction. Field is still from north to south. Which way did we say the current is flowing? You've been told. Into the board, and therefore which way must that thing have moved? Upwards, and we know it was upwards. There's a rule for a dynamo, right hand. The same set of rules, but with a left hand for a motor. I will say you've got a dynamo. Do a few practice examples. Okay. Right. Any other questions? You can use your toes if you want to. Stick to this. Works differently. Don't try. Motor, left hand. Dynamo, right hand. Okay. I'm not going to go into it. We can go into let's have a quick look at why this is so. Okay. The field lines run that way. Do you agree? The field lines around that green current carrying conductor, in which direction is the current flowing? Oh, we're trying to find out which way the current is going to flow. Okay. It's a bit difficult to show in here. I'm moving it. Which way? Did we say? Upwards. So there's no current in that wire yet. Okay? The electrons are stationary. But now if I move electrons up, let's draw this from the top. Okay? Let's draw it from the top. It will look as follows. You'll see the two magnets. North, south. Field lines run in that way. You agree? Okay? You'll see a conductor running across, but I'm moving the conductor up. You agree? So that electron there, which way is it moving? Out of the board, isn't it? So I'm going to represent it with a dot moving that way. Let's draw in red the field lines around that electron, or that stream of electrons. Which hand rule do I use? Right hand rule. Which way is the conventional current? You don't know. Conventional current is into the board because electrons are moving out. Conventional current is opposite to electrons. Okay. So which way is the current then flowing? Into the board. Conventional current is into the board. Electrons are out of the board. So if it's going into the board, my magnetic field is that way. You agree? Okay. What do I get here? Reinforcement, cancellation. So which way is that electron going to move? That way. So conventional current is going to move that way, which we said was into the board because I had an arrow on there. Okay, gets a bit confusing. Okay, that's why be thankful for Mr. Fleming and these two rules. Right, all happy? Right, got it? Okay, let's take this a little bit further and let's look at a dynamo. This lesson finishes in 10 minutes. In fact, I'd like you to turn in your books to a sketch of the dynamo because your book can sketch it much better than I can ever hope to sketch it. I'd like you to turn to page 356. Yes. Yes. Are you seeing me at second break today, Matthew?
I think I can't understand why.
Okay, if you do, that's good. Right, I'm going to draw a dynamo from the top, looking down at it. Okay. You'll have a north pole of a magnet. You'll have a south pole of a magnet. You'll have one coil, and I'm only going to draw one turn on that coil. Okay? Right? And what you've got are complete rings. It's almost impossible to draw. I'm not good enough to draw. Let's keep it simple. Okay, let's have a look at that thing. What have we got here? We've got something that has got a handle attached to it. I've drawn the handle over here. Maybe I should keep it simple and keep the handle away from the split rings. The slip rings, sorry. We take the handle out there and we put the handle here. No, it's not a split ring. Right. Now, a slip ring is not two half rings. What would two half rings be called, Daniel Choi? I think you should come and sit here. Who's sitting here? Then you can stay awake. What are two half rings called, Daniel? What are two half rings called? Commutators. This is a complete circle. So that would be what a slip ring looked like. Okay? Now this wire over here is attached to the slip ring. Okay, it's actually attached. It doesn't just move around. And that wire there is attached to the slip ring. So when this thing turns, the slip rings turn as well. Okay? And your current goes through there and there. Right. Have I got a complete circuit at this stage? No. But I'm going to put, what is that over there? That's a brush. What is this here? That's a brush. And what do I have here in between? A light bulb, an ammeter. Do I put a battery in there? No. Why am I not putting a battery in? Because I'm trying to generate electricity. I'm not making a motor. This is a generator. So I'm trying to make electricity. So I'm going to put, let's put an ammeter in there to keep it simple. Yes?
Why do you have a before you have
Because if the electricity would flow up there to there, then where? How did it get back to here? This is an axle which is made out of wood or plastic or whatever. Okay, so this thing is not attached to this thing. Let's just shade in the axle. Okay, let's just keep it shaded in. Nothing can travel through the axle. The electricity can't travel through it. Happy? It's made out of plastic or wood or whatever. Right. Okay. So, let's say I now start turning the handle at the top. Right. Which way do you want me to turn it? So that this moves out or that this moves in? What do you want? Choose. Okay, you want to move this into the board. And this out of the board. Right. You happy with that? So in other words, if I had a page, that page would turn. If this was my coil, that way. You agree? That way. Right. I want to know in which way is the current flowing there. That's all I want you to tell me. Which hand rule are you using? Fleming's right-hand dynamo rule. Okay? Which way is your field? To the window. Which way is your thrust? Which way is it moving? Into the board. You agree? Which way is the conventional current? Okay. Happy with that? Do it on the other side, please. Which way is the field? To the window. Which way is the thrust? Out. Which way is the current going to move? Up. Right, thank goodness. So that they are working together. Yeah, this one's moving up, around, out here, and then where? You agree? Currents flowing? You agree? Yes.
That would mean that when the coil is like that, I don't know how to.
In the vertical position.
Yes, that would be where the most.
Most or least?
Most is at 90 degrees to the field line. Or is it like a motor? And when it gets
Let's look at it from this side and let's see. If you could put your eye there and look through the magnet, what would you see? You would see magnetic field lines coming towards you. Am I right? Let's draw a bank of them. Do you agree? You'd see a bank of magnetic field lines coming towards you from north to south. You would see this wire running, I'm going to draw it in green, like that. Yes, if your eye was here, you'd see the wire running. Turn this whole thing like that, you'd see the wire. I've just got an imagination.
It's something like when it's at this or when it's like that right now.
Okay, I'll change it to suit your imagination. I think you are. I think you're limited, but let's try and accommodate your... Okay, which way is that wire running? You wanted to run that way. Okay, right. Now, you see, I can't work with your brain on a board which faces this way. You wanting to look this way, and I'd have to...
Wait, have you turned the thing yet?
I've,
This way?
no, I haven't done any turning.
Then this is fine.
You, have you suddenly come online? Did a quick reboot. Okay, now you've confused me completely, but okay, there's that wire. Okay, now that wire is moving into the board, so if we're looking, it's moving down. Okay, do you agree that that wire is, at this stage, if it's moving down, it's cutting across these field lines maximally? So as it is now, it has maximum cutting effect. Once it gets into the vertical position, so now it's cutting across those lines. Think of a wire there, okay? These wires, these lines all running across here like this, and this thing is cutting across them. Once it gets into the board, it's running parallel to those lines. When it gets here again, cutting maximally, okay? And what you're going to find if you had to plot a graph is a graph that looks like this. Are you going to start off now with maximum current or not? Maximum current. When it gets to vertical position, what's your current? 0. Okay? Then it gets around to the other side. Imagine my arms here. Okay? Cutting maximally, no cutting. My head's the axle. That's nice. Okay? Turns around, cut in maximally again. Okay? But as we'll have a look at it tomorrow, it's now running in the opposite direction. Maximum current, but in the opposite, the negative direction, that's the positive direction. And then it goes back to vertical, which gives you 0. Goes back to that position, maximum, and we would think that our graph would look like that. Do you agree? But, as I said, it's not directly proportional. It's just proportional. Your graph actually is a sine curve. But we'll talk about that more tomorrow. Thank you very much.